Today, we're going deep. We're talking about the one architecture that powers just about everything in modern AI. And this isn't just some story about a clever algorithm. No, this is about a fundamental shift in how we teach machines to think, a single idea that truly unlocked the AI revolution.
You know, before the transformer came along, AI language models read things one word at a time, in order. The problem, their memory was like a chain. The longer the chain, the more likely it was to break. Context from the beginning of a long document would just fade away. It was like trying to understand a whole novel by reading it through a tiny straw. Time itself had become the enemy of scale.
And this very limitation, this bottleneck, forced a really revolutionary question, a question that basically challenged the entire foundation of how machines understood language. And the answer to that question was a completely new architecture. It was elegant, it was simple in its core concept, but its implications, well, they were profound. It was called the transformer.
Okay, so let's break this down. We're going to start with the problem that transformers were built to solve. Then, we'll dive into the core idea that makes them so powerful. We'll also look at the hidden costs of that power, and then finally, how these things actually produce the text we see.
Right, so first, let's really get a feel for the world before transformers. Think about old models like RNNs. They process language in a straight line. It's kind of like that game of telephone, right? Where a message gets whispered from one person to the next. By the time it reaches the end of the line, the original meaning is almost always lost or twisted. Well, that's exactly what was happening inside these models. Context just couldn't survive a long journey.
And this brings us to the core breakthrough. The transformer didn't just try to make that sequential chain a little bit better. It completely shattered it. Instead of a single file line, it created a dense network where every single piece of information could talk to every other piece of information, all at the same time.
And this is so crucial to understand. The transformer's main job isn't to read from left to right. Its job is to build a complex internal map of relationships between every word and every other word in the text, simultaneously. It's a relational engine.
So how did it do this? Through a really radical architectural shift. You've got two main parts, an encoder, which digests the input, and a decoder, which generates the output. But the real game changer, the most important part, was ripping out that one word at a time process, what's called recurrence. And getting rid of that is what finally unlocked full parallel processing.
Now, the heart of the transformer, the engine that makes it all work, is this mechanism called self-attention. Here's how to think about it. For every single word, the model looks across the entire text and asks, okay, out of all of you other words, which ones are the most important for understanding me right now? And it's not just a one-off thing. The model uses what's called multi-head attention, which is like having a whole panel of experts looking at the text from slightly different angles, all at the same time, to build a really rich understanding. So when you boil it all down, attention is just a dynamic, incredibly focused way of figuring out what's relevant. For every single step, the model decides what to focus on, constantly shifting its gaze to build a complete picture of the meaning.
Okay, but this whole parallel approach, it creates a really fascinating problem. A paradox, really. If you look at every word at the exact same time, how on earth do you know which one came first? The model just sees a big bag of words, not a structured sentence. It's actually completely blind to order.
This insight right here is absolutely critical. This powerful architecture is incomplete on its own. It has to be explicitly taught the sequence of the language. If you don't do this, a sentence like "the dog chased the cat" looks exactly the same as "the cat chased the dog." The meaning is totally lost.
So what's the solution? Well, it's a really elegant trick called positional encoding. Before the model even starts its work, we add a little mathematical signature to each word, a unique address that tells the model exactly where that word sits in the sequence. It's basically like giving every word a house number on a street, so it knows its position and who its neighbors are.
But of course, this incredible power, this ability for every word to look at every other word, it doesn't come for free. It comes with a pretty steep computational price tag.
Yeah, the cost of self-attention grows quadratically. And what that means is, if you double the length of your text, you don't just double the amount of work, you quadruple it. So a 10-page document isn't 10 times as expensive to process as a one-page document, it's 100 times more expensive. This created a completely new kind of bottleneck, not of time, but of pure computation.
And this framing is really important to grasp the engineering challenge here. A transformer has no memory in the way we do. When it's generating the next word in a sentence, it doesn't remember what came before. It has to reread the entire context and recalculate that entire web of relationships from scratch.
every single time. To get around this insane amount of recomputation, engineers developed a brilliant optimization called the KV cache. You can think of it like a cheat sheet for the model. Instead of rereading everything from the beginning to generate one new word, it stores the essential calculations from the past in a small, fast cache. And honestly, this simple idea is what makes things like real-time chatbots even possible. And this just brilliantly illustrates a core truth about modern AI. Scaling these enormous models is just as much a triumph of clever systems engineering as it is of pure math. It's about how efficiently you can move data around. This is where the real engineering magic happens, with breakthroughs like flash attention, which completely rethought the attention calculation to work around the physical limits of GPU memory. So we have this massively parallel, computationally intense machine all figured out. But how does it actually, write something? Well, it isn't some magical act of creation. It's a very structured mathematical process of picking from a field of possibilities.
It's really a three-step dance. First, the model generates a raw preference score for every single word in its vocabulary. These scores are called logits. Second, a little function called softmax comes in and tidies up those scores, turning them into clean probabilities that all add up to 100%. And then, finally, the model simply picks a word based on that probability distribution. But how it picks that word matters a lot. If it just greedily grabs the most likely word every single time, the text becomes really robotic and repetitive. But smarter techniques, like nucleus sampling, do a much better job of mimicking how humans actually write, with a nice mix of predictable words and the occasional creative surprise.
And this is really the final piece of the puzzle to understand. The model isn't a machine that chooses the one correct word. It's a probabilistic engine. It navigates a vast landscape of possibilities, and it constructs its response one sample at a time.
So when you put this all together, you can see exactly why this architecture didn't just get a little bit better, it completely took over. It was built from the ground up for the parallel chips in our GPUs. It could finally understand relationships across huge documents. It made the whole idea of pre-training and fine-tuning incredibly effective. And the core idea of attention, it was so general that it works for images, for audio, for everything.
And really, this is the ultimate takeaway. The victory of the transformer wasn't because it was some kind of smarter algorithm in a vacuum. It won because it was an architecture perfectly designed to ride the massive, exponential wave of more data and more computing power. And today, the legacy of that single architectural leap is absolutely everywhere. From the language models that help write our code to the AI that generates images from a text prompt. They all stand on this one foundational idea: attention over sequence.
Thanks for joining this explainer. Join us next time when we explore what happens when you take this incredibly scalable architecture and you feed it the entire internet, pushing it to the very edge of what we might call intelligence.